we're going to consider a boiler, which has an input stream that is at a low temperature, and obviously we'll have an output stream at a higher temperature due to heat transfer that occurs in the boiler. We're told that the mass flow rate at the inlet is 5,000 kilograms per hour. I know that it is a mass flow rate because the units are mass per time, or mass flowing. The pressure is given to me as 5 megapascals, and the temperature is given to me at 20 degrees centigrade. Before I continue, I will circle these two fellows. I know everything about the thermodynamic state at 1 if I know 2 independent intensive thermodynamic properties. At state 2, I'm told that indeed the temperature has increased. It's now 450 degrees centigrade, whereas the pressure has dropped a little bit. Typically, boilers are considered to be idealized as isobaric, meaning that the inlet and outlet pressures would be the same. In fact, we are going to expect that the pressure will drop. If I want to push water from here to here, the pressure here should be lower than the pressure here. The reason for that is I have to overcome the frictional losses that would occur as I'm pushing water through the boiler. If there were no frictional losses, it indeed would be perfectly isobaric. I again circle my 2 given properties at state 2, knowing that all of the thermodynamic properties at that place are known now. We're asked to find the diameter at the inlet and at the outlet if the velocity has to be less than or equal to 20 meters per second at both locations. We can see before we begin that this is not a blob problem, but it's a control volume analysis, and indeed we are told that it is water as the working fluid in this boiler. So let's write down some governing equations for an open system, and in this case we only need to really consider conservation of mass. Conservation of mass says that the total rate of change of mass inside my control volume is equal to the mass flow rate in minus the total mass flow rate out. In this case, we know that there's really only one inlet and there's only one outlet. It's a good approximation at this point to assume that it's at steady state. What does steady state mean? It indicates that if I were to take a picture of this with some kind of camera that was able to see inside the boiler, and I were to overlay a picture at another time, they would look the same. I might have spatial variation, but the temporal variation is minimal. I don't have any change of the amount of mass inside my boiler between the 2 times. So the amount of matter in here is the same, but the actual particles of H2O are changing, of course, as water goes in cold and comes out hot. Lastly, we need to write down our helper equation that we always write down. The mass flow rate at any given location is the density there times the velocity at that location times the cross-sectional area of the water that would be flowing. Lastly, we can see that we better write down an equation of state. For water, we always use the tables, and we need to find the phase at each one of these states in order to make this happen. We know that the mass flow rate at 1 would have to be equal to the mass flow rate at 2 due to conservation of mass at steady state, so it's better to just write down that we only have really one mass flow rate in this problem, and it is given by 5,000 kilograms per hour. At state 1, we know the pressure and the temperature, and we know the mass flow rate. We also know, therefore, the density at 1. So at state 1, I know the mass flow rate, I know the density. I could find the area associated with a particular diameter. The area is known by geometry as pi on 4d squared for a pipe, a circular pipe. First, find the phase. We would draw the PT picture, the vapor pressure curve, knowing that over here we have liquid, and underneath the curve we have gas. This is the critical point. We are indeed a liquid in the tables. So given that we're a liquid, we use table A7. And we would find that the density is just 1 over the volume at this state, which in our case is going to be 1.004 times 10 to the 3rd kilograms per meter cubed. Let's also do the same thing for state 2. Again, looking at the vapor pressure curve, what do we find? This time our temperature has increased a great deal, our pressure is diminished. We are actually over in the gas regime. If we look at table A4, A5, for gassy water, what do we use? We use table A6 is our equation of state. And we simply look up this value. Rho 2 is going to be 1 over the specific volume at 2, which is just 14.1323 kilograms per meter cubed. We see a massive change in the density. So liquid is very dense, about 1,000 kilograms per meter cubed, as we would anticipate, whereas the density of gassy water has diminished or has decreased a great deal. So what does this mean for the diameters at each place? We know that our mass flow rate is equal to 5,000 kilograms per hour, which we can rewrite dividing by 60 twice as 1.3889 kilograms per second is equal to rho VA at 1. This is just going to be rho V pi on 4 times d1 squared. Solve this for d1. 4 on pi times the mass flow rate over rho 1 times the velocity at 1 to the 1/2. So what we see in this equation right here is the diameter and the velocity are related, and as the velocity increases, the diameter would have to decrease, and as the velocity would decrease, since this is the denominator, the diameter would have to increase. For 20 meters per second, plugging in all of our numbers, we get that the diameter here would be 0.009401 meters, or 9.401 millimeters. For the velocity to be 20 meters per second or lower, I would have to have a diameter that's 9.401 millimeters or greater. Similarly, the mass flow rate at 2, plugging in my numbers again with the velocity assumed to be 20 meters per second, gives me 7.910 centimeters or larger.